Hello everyone. So in this video we'll discuss class A amplifier. So in the previous video we discussed different types of power amplifier. So now we'll discuss class A power amplifier. Okay. So class A power amplifier is further classified into series fed directly coupled power amplifier and transformer coupled power amplifier. So why it is called series fed or directly coupled amplifier is the load is directly connected to the transistor. So whereas in the transformer coupled, so the load is coupled to a transformer, coupled to the collector through a transformer. Okay, so the class A amplifier is divided into two types: series fed directly coupled power amplifier, class A power amplifier, and transformer coupled class A power amplifier. So in this case load is directly connected to the transistor here, that is to the collector. Here the load is connected to a collector through a transformer, so that is why it is called transformer coupled class A amplifier. So today we'll discuss series fed class A amplifier and we'll define and we'll derive. So what is the series fed and what is the efficiency of the series fed class A amplifier. So we'll see the circuit of series fed class A amplifier. So we have a transistor, load RL is connected to a collector, so this is V in, okay, that is giving a AC signal, and emitter terminal is, so this is VBE, and we have connected VCC, and this is RB, and this is IB. Okay, so this is the circuit of a series fed class A power amplifier. So we'll see. So what is the DC bias operation? That is, when we applied a DC voltage VCC, what are the current and the voltages? So by applying DC bias, so we'll get, so by applying DC bias, IB will be VCC minus VBE divided by RB. So this we have studied previously only. IB is equal to VCC minus VBE divided by RB. Okay, so what is VBE? VBE is always 0.7. That is VBE minus 0.7 divided by RB. So the collector current. The collector current will be IC is equal to output current. So IC is equal to beta times IB. So what is the output? So voltage. So output voltage is VC. VC is equal to VCC minus IC RC. Okay. So these are the three terms we do get when we bias our series fed class A amplifier. Okay, so the output current IC is equal to beta times IB. So output voltage VC is equal to VCC minus IC RC. So we'll see the DC load line. So when we apply a voltage VCC, so these are the parameters we get: the output current, output voltage, and the current IB. Okay, so DC load line. So DC load line is we apply the output voltage versus output current. So our output voltage is VCE, our output current is IC. Okay, so the load line should intercept the x-axis and the y-axis. Okay, so VCE axis intercept, so at what is this point? So when a DC load line intercept this point, what is this point we call, will determine now. So we have the equation VCE is equal to VCC minus ICRC. Okay, to find the intercept of the y-axis, that is VCE, we need to make IC is equal to 0. Okay, IC is equal to 0. Therefore, what VCE become? VCE will become VCC. Okay, so this is the point of the load line where it intercepts x-axis, that is VCE. So that will be equal to VCC. Okay, when IC is equal to 0, so VCE is just VCC. That is when no current inside the transistor, our output current is just VCC. Okay, to find the y-intercepts, we need to make VC is equal to 0. So VC is equal to, if in this equation we apply VC is equal to 0, so IC will be VCC divided by RC. Okay, so VCC divided by RC. So this is the point where VCC divided by RC. So this is the, now we can draw a load line between the x-axis and y-axis. So so this is the 2 points between the x-axis and y-axis we have found. Now we need to find, so where is the Q point, that is the DC operating point should be there. So for the transistor to operate in the active region, so we should have the DC load line at the mid of the the Q point at the mid of the DC load line. Okay, so now, so if you draw the 2 lines between these two, so we'll call it as this as ICQ, we'll call this it as VCQ. Okay, so this is the point where this is the DC current and this is the DC voltage. Okay, now, so now we'll see the AC operation. Okay, so when what happens when an input, so till now what we discussed or what we wrote, what we have defined, everything was when this AC signal is not applied. Okay, so when the AC signal is applied, so bias current, so the base current will vary. So okay, so the base current, so when you apply a small input signal, so since we are applying it to the base of a transistor, the base current will vary above the DC bias point. So above this point the base current will vary. So if the base current varies, the collector current will vary. So if this varies, the collector current will varies and VCE will also vary. Okay, so if IC varies, VCE will also vary. So if the input signal is made larger, so since the transistor, if the DC bias point is at the mid of the load line, the transistor will act as an amplifier. Okay, so if we give a small signal, so we'll get a amplified signal. Okay, so now what is the maximum current or voltage that swings between the x-axis and the y-axis? Okay, so when you apply a voltage, when you apply an input signal, so the maximum that can vary, the maximum current can vary from this point, to I minimum. So this is our I minimum. So I'll make this. Okay, this is I minimum, this is I maximum. Okay, so the maximum IC can be VCC divided by RC. Okay, so the maximum VCE can be just VCC, and our output voltage will also vary from the DC point, that is from here to here. So this, okay, so that is, here we can say V maximum can vary to up to VCC, I maximum can be vary to VCC divided by RC. So I minimum can be 0, V minimum can also be 0. That is, when you apply an input signal, VCE can vary from 0 to VCC. So upon this it can't vary. So it will go to saturation region. So when I minimum, so the collector current IC can vary from 0 to I max. So this is the biasing. So this is ICQ. So if you put a graph on this, or if you calibrate this, so this is the current, and that means at this current and this DC voltage and this DC current, our transistor will work as a amplifier. So this we have set DC ICQ and VCQ. Now if you put an input signal and start varying, so you will get, this is the output signal what I am discussing. Okay, so the output signal can vary from 0 to maximum I max, that is VCC divided by RC. The VCE can vary from 0 to V max, that is V minimum to V max. This is I minimum to I max. What is I minimum? 0. What is I max? VCC divided by RC. What is minimum VCE? 0. What is maximum VCE? VCC. Okay, so if this is ICQ, so from here to here it is ICQ. Okay, so what is this? Then from here to here it is 2 times ICQ. Okay, so this is 2 times ICQ. Okay, so now we need to analyze few more things. Okay, so suppose if this is the voltage or current signal. Okay, so we call from here to here it is peak to peak value, that is from maximum, whether it is I or V, maximum and minimum. Okay, so VP, that is, let me take V only, V max, V min. So V max, from V max to V minimum, that is V max minus V minimum, we call it as V peak to peak, that is peak to peak voltage. Okay, so only from 0 to V max we call it as VM, or only from 0 to V minimum we call it as VM. Okay, so only from here to here it is VM, from here to here it is also VM. Okay, now what is V max minus V min? So V max minus V min is VPP. But what is VM now? So VM is V peak to peak divided by 2. Okay, so if we want only this voltage, and from 0 to this voltage, if we want, we need to divide V peak to peak divided by 2. Okay, so from here to here it is VM. Okay, to get VM we need to divide V peak to peak by 2, that is V max minus V min divided by 2. If I divide this, I'll get VM. Okay, so now we'll see what is our DC power and what is our IC power. Okay, so now the DC power PIDC is given by, so DC power PIDC is given by VCC into ICQ. Okay, so PIDC is given by VCC into ICQ. Okay, so VCC. So what is ICQs? So from this figure you can observe ICQ. Okay, so ICQ is only this much. From here to here is ICQ. That is from this point, whatever it is varying, that is ICQ. Okay, from here to here it is 2 ICQ. So what you can write? So ICQ, that is ICQ now is nothing but IM. Okay, from here to here it is ICQ. From here to here it is 2 ICQ. I have not written 2 ICQ. Okay, so now from here to here is ICQ or IM. In other words, IM. Okay, so for ICQ we can write IC peak to peak divided by 2. So ICQ is nothing but IM, I'll write. In other words, we can say IM. Okay, so but what is IC? But IC is equal to VCC into RC. So I can write VCC into VCC RC peak to peak divided by 2. That I can write V square CC RC divided by 2. Okay, so this is our input power, DC input power. Okay, so what we have applied. So we'll see what is DC output AC power. Okay, output AC power. So this is the DC. So what input we are giving is DC. So output what we are getting is AC. So output AC power is, so output AC power is given by VM into IM divided by 2. Okay, so VM into IM divided by 2. But what is VM into IM? So I have already told VM is V peak to peak divided by 2 into IM is I peak to peak divided by 2 whole divided by 2. So that is, what is V peak to peak? So I'll just split this. V peak to peak into I peak to peak divided by, so if I take multiply this, 2 2s are 4, so 8 I'll get. Okay, so what is V peak to peak? So I have already told V peak to peak is V max minus V min into I peak to peak is I max minus I min divided by 8. So this is my output power, output AC power. So in other words, I can write, so POAC is, what is V peak to peak? So maximum VCE peak to peak is how much? Okay, so maximum VCE peak to peak is VCC. Okay, what is maximum I peak to peak? So if I take maximum I peak to peak is VCC divided by RC divided by 8. So that will become V square CC divided by 8 RC. Okay, so that is PAC. Now, so I'll write here, what is the efficiency? The efficiency of an amplifier can be defined as output AC power to the input DC power. Okay, So what is output AC power? So output AC power is, have divided V square Cc divided by 8 RC. What is input power? V square Cc divided by V square Cc into RC divided by 2. Okay. So if I solve this, V square Cc divided by 8 RC into 2 divided by V square Cc into RC. Somewhere so this RC will go up. V square divided by 2 RC. Here I have written wrong. Okay, so this RC will go up. So RC will get cancelled. V square CC will get, so 1 by 4. So eta is equal to 1 by 4. So into 100. So therefore eta is equal to 25%. 1 by 4 is, so class A power amplifier efficiency is 25%. Okay, so in other words I can write using this equation. So Vmax minus Vmin divided by Imax minus Imin divided by 8. So using this you can write. So what we have got? So PAC is it? PAC is equal to Vmax minus Vmin into Imax minus Imin. Okay, so from this diagram you can observe what is Vmax. Vmax is just VCC. Vmax is VCC. What is Imax? Sorry, what is Vmin? Vmin is 0. What is Imax? Imax is VCC divided by RC. What is Imin? Imin is equal to 0. Imin is 0. Imax is VCC divided by RC. So if I apply this here, I'll get PAC as Vmax is VCC minus Vmin is 0. Imax is VCC divided by RC. Imin is 0. Okay, divided by 8. So I'll get it as V square Cc divided by 8 RC. This is PAC. What is PDC? So PDC is just VCC into ICQ. So if I take this, now eta is PDC output, sorry, PAC divided by PAC is V square Cc. So somewhere I have done wrong, I guess. Okay. Imax is VCC divided by RC. This I can write it as 2 ICQ. Okay. So that if I apply, so Vmax is, I can write 2 ICQ because I need in terms of ICQ. Therefore, this I can write as what? VCC, this I can write it as VCC into ICQ divided by 8. Okay, so now this is PAC is VCC into IQ, 2 IQ divided by 8, so PAC is, PDC is VCC into ICQ. Okay, so this will cancel. IQ 2 by 8 is, eta is equal to 2 by 8 is 1 by 4, that is 25%. So the series FET class A amplifier has an efficiency of 25%. Okay, so they'll ask for the derivation. So prove that the maximum efficiency of a series FET class A power amplifier is 25%. So you need to draw the circuit to say what is the DC bias point, so how the load line you'll get, so what is the maximum AC current and the output, and you need to take taking efficiency, etc. Okay, thank you.